We're going to change gears again here now and talk about another one of Newton's laws. This one's called his third law. I want you to look at the picture up on the board here first, though, before we start talking about the law itself. These two cars that look remarkably like each other are going to collide. Presumably, they have the same mass. Presumably, they have the same speed when they hit each other. What happens when they hit each other? Well, they probably get wrecked. Why? Because they apply a force on each other. What do we know about the force that object 1 applies on object 2? Yep. It's equal and opposite to the force that object 2 applies on object number 1. So both of these objects slow down and probably stop. Both of these objects get deformed as a result of the equal and opposite force that acts on them, right? That is Newton's third law, the way you've heard it stated before. For every action, there's an equal and opposite reaction. For every action, there's an equal and opposite reaction. Now, I want to tell you why I don't like stating it that way, why I don't like stating Newton's third law as for every action, there's an equal and opposite reaction. Let's say we've got these two cars again, but I want to simplify it a little bit. Car number 1, and I've got car number 2. This time the masses aren't necessarily the same. Maybe they are, maybe they're not. It doesn't really matter. I want you to draw, I want somebody to come up here and draw for me a free body diagram for object number 1. Remember, object number 2 is there. I just don't want to have this diagram cluttered right now. Okay, object number 1 collides with object number 2. Draw the free body diagram on object number 1 as it collides with object number 2. Thank you for volunteering, Everett. Everett's going to draw a free body diagram for object 1 as it collides with object 2. We just don't have object 2 drawn there because we don't want to clutter the diagram up. We're drawing a free body diagram for only object 1. Okay, we know there's an equal and opposite force, right? But we're ignoring object number 2 right now. Okay, go ahead. We'll draw all the forces that act on, And again, doesn't matter where we draw them, right? Front, back, below, above, doesn't really matter. Okay, he's drawing one force there. He's drawing another force there that's equal and opposite. Okay, for every action, there's an equal and opposite reaction. He's going to call this one F. Okay, Fi, you can call it Fi if you want. Okay, FC, F collision. It's all okay. It's all good. Any more forces there, Aiden? Everett, I mean. Okay, he's got a normal force and a force of gravity there. Okay, force of gravity down, normal force. We don't know how big those should be relative to Fi and FC, right? Okay, we know they should be the same length. Is that good, guys? Good. Have a seat, Everett. Thank you. Is that a good free body diagram for object A, object number 1, as it collides with object number 2? Let's start canceling off some forces, right? Because we can do that. These two are equal and opposite. We can get rid of those, right? These two are equal and opposite. We can get rid of those, right? What's the net force acting on object number 1? 0. If the net force acting on object number 1 is 0, explain to me why this car slows down. It hits the other car. There are equal and opposite forces acting here, but this car, as it experiences these forces that Everett's drawn, slows down and stops. How can it slow down if it's in translational equilibrium? And that's what it's in, right? If all the forces balance, it's in translational equilibrium. How does it slow down? This is why I don't like stating Newton's third law is for every action, there's an equal and opposite reaction. Because when you state it that way, it leads to this misconception. I didn't care who I picked to come up to the board and draw this. Okay, I was confident that whoever I picked would draw it this way. This is the way that I wanted you to draw it. I set you up to draw it this way, but it's wrong. It's wrong because the forces can't possibly balance on this object, otherwise it wouldn't stop. So how do we fix this? Let's restate Newton's third law. Not for every action there's an equal and opposite reaction, because I don't want to make this mistake. I want to state it in the following way. If object A applies a force on object B, then object B applies an equal and opposite force on object A. It's the same thing, right? It's the same thing, but it clarifies that we're talking about two different objects here. If object A applies a force on B, object B applies an equal and opposite force on object A. How should this diagram really look? It should look like this. That other force shouldn't be there. Why shouldn't that other force be there? Because it's on the other object. There was a force acting on object A, ever call it FC. But there's also a force acting on object B. Let's call it FD or whatever we want, right? There's two equal and opposite forces, but they act on different objects. So they don't cancel out. They don't balance out because they're not acting on the same thing. If we say for every object there's an equal and opposite, for every action there's an equal and opposite reaction, we forget that a lot. Okay, I'll tell you what, most people would hear Newton's third law, for every action there's an equal and opposite reaction, which by the way is correct. It's stated correctly. I just don't like stating it that way. Most people hear that and think, oh, that's the easy one, right? Newton's first law, that's kind of the one hard to understand, right? Translational equilibrium, static equilibrium, and slowing down, speeding up. That's a hard one to understand. Newton's second law, oh, that's an equation. I don't like math. That's a hard one. Newton's third law, for every action there's an equal and opposite reaction. Oh, that's the easy one, right? No, it isn't. Newton's third law, I think, is the hardest one. If you really dig deep into it, it's the hardest one because probably every single one of you would have made that mistake. We're going to state Newton's third law in the following way. If object A applies a force on object B, then object B applies an equal and opposite force on object A. You get up in the middle of the night to go to the bathroom. What happens sometimes? It's dark. You're walking around your bedroom. You got to walk out the door to go to the bathroom. And all of a sudden, as you go past the end of the bed, you stub your toe on the end of the bed, the bedpost. What happens? It hurts, right? Why does it hurt? Because you stubbed your toe. No, it doesn't. It doesn't hurt because you stubbed your toe. It doesn't hurt because you kicked to the end of the bed. It hurts because the bed kicked you back. If object A applied a force on B, B applied an equal and opposite force on object A. You kicked the bed. If that's going to do any damage, it's going to do damage to the bed, not your toe. The bed kicking you back is what does damage to your toe. Here's another one. You punch a piece of glass. You apply a force on the glass. Oh, wait, this is a little bit different. This time we're breaking the glass. Is there an equal and opposite reaction force now? If I apply a force of 100 newtons on the glass and it breaks, I think we'd all agree if the glass doesn't break, then I apply a force of 100 on the glass applies an equal and opposite force of 100 back on me, right? If it doesn't break. But if it breaks, does it apply that equal and opposite force back on me? How many people say yes? How many people say no? If it breaks, the force is going to be less. Okay, it's about 50-50. One person voted yes, and one person voted no. The forces are still equal and opposite. Newton's third law is not dependent upon something breaking or not breaking. It's dependent upon nothing other than the interaction between the two objects. If object A applies a force on object B will always, every single time, it's happened every single time in the history of the world, object B will always apply an equal and opposite force on object A. So how do we explain the whole breaking thing? When I punch the glass and apply a force of 50 newtons, the glass breaks. How can it possibly apply a force backwards with the same value? Now here's the deal. After it breaks, it's not. But I'm not applying a force on the glass after it breaks. I applied a force on the glass of 50 newtons. It applied a force back on my hand of 50 newtons. 50 newtons was enough to break the glass. 50 newtons wasn't enough to break my hand. It was still the same force. It's just that It happened to be enough to break the glass. It wasn't enough to break my hand. Say I throw a rock through the window, throw a big rock or a big cinder block or a big brick through the window, and it smashes it. And the brick keeps going. Is that equal and opposite forces? Brick applied a force on the glass. Does the glass apply an equal and opposite force on the brick? Yeah, every single time in the history of the world. Object A applies a force on B, B applies an equal and opposite force on A. How do we explain that one? Well, the brick applies a force, let's say, of 100 newtons on the glass. That's enough force to break the glass. It's not enough force to break the brick. The brick keeps going. Why? Because 100 newtons might have been enough to slow down the brick, but it wasn't enough to stop the brick. So for the time they were actually touching, there was enough force to break the glass. For the time they were actually touching, there was enough force to slow down the brick. Remember what forces do? They can deform an object, break the glass, or they can accelerate an object, slow down the brick. Does that make some sense? Let's just do a couple quick little math things and then we'll wrap it up for the day. Mr. Dickie's mass is 70 kilograms. Everett's mass, we're just going to call him Ev for short. That's what all his fans on the internet call him, right? Ev. Ev's mass is, what's your mass, Ev? Let's say 65 kilograms. 65 kilograms. Ev pushes Mr. Dickie, causing him to accelerate at 2.5 meters per second squared. What's Ev's acceleration? Well, we know that if object A applies a force on object B, then object B applies an equal and opposite force on object A. Let's sub in M times A for those two forces. The mass of object B times the acceleration of object B is equal to negative, because it's equal and opposite, mass of object A times acceleration of object A. 2 seconds here, 70 kilograms, sorry, 65 kilograms for Everett. His acceleration is whatever. My mass is 70 kilograms. My acceleration is 2.5. Let's calculate this now. Let's say 70 times 2.5, negative 70 times 2.5 gives me 175. Negative 175 divided by 65 gives me negative 2.7. Couple things. First of all, why is Everett's acceleration negative? Because it's got to be opposite to my acceleration. He goes forward, I go backwards. Second of all, why is Everett's acceleration more than mine? Same force, right? Why is his acceleration more than mine? Because he weighs a little bit less, right? Good. That's it for today, guys. Finish up those questions that I assigned earlier for homework, and then you're good to go.